Hey guys, this will be the video for the 5.8 5.9 homework. Okay, so the function f is continuous on the interval from 0 to 16. F is twice differentiable, and at x equals 3, the derivatives are undefined. Information about the first and second derivatives of f for values of x in the interval from 0 to 16 is given in the table above. At what values of x in the interval from 0 to 16 does the graph of f have a point of inflection? So point of inflection is going to be when f double prime of x changes signs. So let's look here. So we have the second derivative. It is positive. Then it's undefined at x equals 3, and then it is negative. So that's going to count as a point of inflection at x equals 3. And then it's negative, then it's 0, then it's positive. So at x equals 9, that's going to count as a point of inflection. And it's going to be 0 here, but it stays positive. And so that's got to be B. Okay. 2. Let f be the function defined by f of x is equal to 1/3 x to the third minus 3x squared minus 16x. Which of the following intervals is the graph of f both decreasing and concave down? So decreasing means that f prime of x is going to be negative, and concave down is going to mean that f double prime of x is also negative. So that's what we're going to check for. So let's find f prime of x. That's going to be x squared minus 6x minus 16. I'm going to set that equal to 0. That's factorable, I think, I hope. Sorry, is that? Yeah, it's minus 16. So minus 66, negative 16, so that's going to be x minus 8 and x plus 2. So x equals negative 2 and positive 8. So if I think about the first derivative test, okay, so if we have negative 2 and 8, I'm just going to go based off of what I know. This is a cubic function, so it's probably going to go something like this right here. Okay, and that's where it's equal to 0, right? So it's going to be decreasing in between here. It's maybe a little bit of an assumption because it might not. It could look like this right here where, I don't know, where there could be shelves, I guess I'm saying, but I'm just going to assume that there isn't. So I'm going to assume that it's decreasing from negative 2 to 8. So the first part, from negative 2 to 8, it's decreasing. The second derivative of x is going to be equal to 2x minus 6. I'm going to set that equal to 0. So 2x is going to be equal to 6. That means x is going to be equal to 3. So that's where potentially it changes concavity. So then, again, if I just think about the graph of x to the third, okay, it's probably looking like this, where the concavity is happening at x equals 3. So it's going to be concave down, then concave up. So it's going to be down and then up. But again, it's really not too hard. If this right here is going to be equal to 3, if I plug in something like 0, you can see it's negative. And then if I plug in something like 4, that'd be 8 minus 6, which would be positive. So it's concave down here. So it's going to be concave down from negative infinity to 3. So where is it going to be both decreasing and concave down? And so if we think about that right there, both, so decreasing, it's going to be decreasing and concave down from negative 2 to 3. So B. There you go. That's where those intervals intersect, or cross over, I guess you could say. All right, the first derivative of function h is given by h prime of x, and the second derivative of h is given here. On what open intervals contained in -3 to 2 is the graph of h both increasing and concave down? So this is a graphing calculator. So let's say increasing. Let's go ahead and use our graphing calculator and figure out where it is increasing. And so let's go to y equals, clear that out, and then I'm going to graph h prime, which is sine of x, and then plus cosine of x squared. Okay, let's graph that right there. Window, let's change the window to be from -3 to 2. Wow. Okay, so where is it increasing? So that's going to be when it's whenever this is h prime, so when it's above the x-axis. So we're going to want to use the 0 function here and locate these zeros. So -2.728. So -2. What was it? -2.728. To -2.347. Okay, I don't see any of those numbers here, by the way, so I'm going to assume it has nothing to do with it, but let's try these other ones. Oh my gosh. Second trace, 0. So let's do here, enter, and enter. That's -0.85. Still don't see that value here. Okay. And then, I don't like this right here. $1.727. This is concerning. Okay, now I also see that it's gonna be above the x-axis, just at the very right. So, enter. Dude, 1.849. I think I was looking at the y values. Was I? I think I was looking at the y values for that last one. Hold up. So no, not that one. I looked at the here. No. I was looking at the x values. Okay. Do I have everything typed in correctly? No. I forgot the plus x, dude. Are you kidding me? Oh, man. Where are you guys when I need you? Alright, so we only have one value of x. That's at -495. I'm going to make sure that this is so sine of x plus cosine of x squared plus x. That's the first derivative. So left bound. So -495. All the way to the end of the interval, so that'd be 2, not infinity. Right? Okay. So that's where f is, or h is going to be increasing. But where is it going to be concave down? So let's graph h double prime. So h double prime is cosine of x, and then we have -2x sine of x squared plus 1. Okay. Let's see. I don't think I need to worry about the left side of this graph since... Second trace. I'm just going to focus on this one right here. So enter, enter. So 9, 6, 9. And then... So the reason why I'm not checking the zeros on the left side is because it wasn't... Whenever I graphed h prime, none of the intervals were on the left side of the y-axis, and so that's why I don't think I need to bother with it. And then 1.697. Okay, and so this is where h is concave down. And where do these overlap? They overlap. So if I had like a number line right here, this is negative 0.495. And then 2. But these values are, so that's in between. These values are in between. So it's just going to be where it's concave down. And so that's going to be this one right here. And there we go. All right, for number 4. The function f is differentiable and increasing on the interval from 0 to 6. So that means f is always going up. Okay? The graph of f has exactly 2 points of inflection on this interval. Which of the following could be the graph of f? So if I look at this one's always increasing. It can't be b. Wait a minute. 1, 2, 3, 4, 5, 6. So it can't be b because we're decreasing right here. So I know it's not going to be that one. Oh, wait a minute. Which of them could be the graph of f prime? Sorry, I thought these were the graph of f. So that's different. Which of these could be the graph of f prime? So graph of f prime has 2 points of So the graph of f has 2 points of inflection, meaning that so if the graph of f has 2 points of inflection, so if we think about like the line right here, 2 points of inflection meaning that it's changing concavity at 2 different times, and that could be negative, positive, negative, or positive, negative, positive, but essentially meaning that f prime what does that mean about f prime? Has exactly 2 points of inflection. What's the following could be the graph of f prime, the derivative of f? So remember that f prime, so if f prime is increasing, that means it's concave up. If f prime is decreasing, that means f is concave down. So if f prime is increasing, f is concave up. If f prime is decreasing, then f is concave down. And so there needs to be, for the graph of f prime, since there's 2 points of inflection on f, that means it has to have increasing, decreasing, increasing. So the graph of f has to change from increasing to decreasing or decreasing to increasing twice. It has to happen twice. And so this is the graph of f, and it doesn't change from increasing to decreasing. So it can't be that one. This is for this. So does that make sense? Hopefully that makes sense. So if this is f prime, okay, because this is only increasing, and if f prime is only increasing, that means f is always concave up, right? Okay, and then here f prime is increasing from here and decreasing here, so this means that f is going to be concave up and then concave down. This is just concave up for the graph of f. for here, so it's the graph of f is going to be concave up, concave down, then concave up, which would give us 2 points of inflection. So here, 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 this would be up, down, but this would mean that there would be 3 points of inflection. So it's got to be C. Yeah, okay. It's got to be C. 2 points of inflection. Cool. All right, for 5, the graph of f prime, the derivative of f is shown in the graph. So this is f prime. Which of the following could be the graph of f? So if it's f prime, let's think about this right here. So think about this right here. This means f is decreasing, and then it's increasing. And then f is decreasing again. So this right here, because this is where f prime is positive, that means f is going to be increasing. So increasing, increasing, decreasing, increasing, decreasing. And then, so no. I don't think I have this right. Did I? I'm telling you, this really gets your brain working here. So if f prime is positive, means f is increasing. And I think I had it differently. So f is increasing. F is decreasing in between here, and f is increasing because f prime is positive, f prime is positive, f prime is negative. So we need to look for a graph where it's increasing, decreasing, increasing. So this is decreasing, increasing, decreasing. No, this just means that it's always increasing, which it's not. And this is decreasing, increasing, decreasing, increasing. So no, it's got to be C right there. So f is increasing. You can see that's increasing here, and then it's decreasing, and then it's increasing. Yeah. All right, for 6, the graph of f double prime, the second derivative of f is shown above on the interval from 0 to 8. Which of the following could be the graph of f? And so this means right here that f is concave up. This is going to be concave down from there to there and concave up. So there's got to be 2 points of inflection. So this right here is concave up until maybe like somewhere in between here. So this has 1 point of inflection. That's an inflection point. So this is concave up, and then it's concave down somewhere in here, point of inflection, then down, then up. So that has 2 points of inflection. So it could be that one. This is concave down, then somewhere in there it's got to change. Concave up, then maybe like somewhere. So it could be that one, I guess. And then concave up, somewhere changing from concave up to concave down, somewhere there. It's not going to be D. It's not going to be A. So it's between B and C. So it's between B and C. So this is the graph of f double prime. So maybe somewhere after 2. So yeah, it's got to be C then, because if those are going to match up with the x values. So somewhere after 2 is where it changes concavity, and somewhere after 5. And yeah, so 1, 2, 3, 4, 5, 6. No, it's not going to be B. It doesn't line up, so it's got to be C. All right, and for 7, we've got a free response question. All right, so for 7, let's see. So we have a graph of f. Fill in the missing entries in the table below to describe the behavior of f prime and f double prime. Indicate positive, negative, or 0. Give reasons for your answer. So f prime from -5 to 3. So from -5 to 3, f prime is positive. Yeah. From -3 to -1, so from -3 to -1, f prime is negative because f is decreasing. So negative, and you can see that the graph is still positive. The graph is always positive, and then it's going to be positive because we're increasing, and then we're going to be decreasing, so f prime is going to be negative. F double prime, so f double prime, we're going to say that the second derivative is just 0 from -5 to -3 because there is no concavity. And if there's no concavity, that means the second derivative is 0. And then from -3 to -1, and also from -1 to 2, it's going to be positive, concave up. And then 0 because no concavity. Okay, there is no value x in the open interval from -1 to 5, from -1 to 5, at which f prime. Explain why this does not violate the mean value theorem. So the mean value theorem, so let's state the conditions of the mean value theorem. So the mean value theorem has I guess you could say 3 conditions, but 1, I guess you could say it's continuous, 2, differentiable, 3, closed interval. And then the thing is from -1 to 5, it is continuous, but it's not differentiable at 2. So f is not differentiable at x equals 2. Explain why this does not violate. So there is no value. Well, okay, so this is the average rate of change, right? So there's no point in the interval from -1 to 5 at which the instantaneous rate of change is going to be equal to the average rate of change. And so, right, that's because it's not differentiable at 2. So that is our reason. F is not differentiable at x equals 2, so that's why it doesn't violate the mean value theorem. It's because the conditions aren't even met. So this is not guaranteed then. So yeah. All right, C, find all values of x in the open interval from -5 to 5 at which the graph of G has a point of inflection. Explain. So fine. That's find all values of x in the open interval from -5 to 5 at which the graph of G G which the graph of G has a point of inflection. Okay, so that means we need G double prime. So G double prime of x. So first of all, G prime of x is equal to f of x. G double prime of x is going to be equal to f prime of x. And then we want to know when f prime of x is not only equal to 0, but will change signs. So that's when G is going to have a point of inflection. So when does f prime of x equal 0? So f prime when is the slope going to be equal to 0 here? Slope is going to be equal to 0 at x equals -1. So x equals -1. And then you can see here that the derivative, so f prime, so if this is f prime of x, so because g prime is equal to f of x, and then g double prime is equal to f double prime, so the slope of this graph, it's 0 here, negative then positive, so there is a point of inflection right there. So the point of inflection is at -1. So f prime changes from negative to positive. So G has a point of inflection at x equals -1. Yep. Okay, and D, at what value of x does G attain its absolute maximum on the closed interval from -5 to 5? So when does G attain an absolute maximum? So that sounds like it's the candidate's test. So when does G prime of x, which is equal to f of x, equal 0? Okay, and then we also have the endpoint. So we're gonna be using the candidates test, right? At what value of x does G attain its absolute maximum? So we got -5 and 5. And then if we want to know the absolute maximum, we need the critical points. That's going to be when G prime is going to be equal to 0. That's when f is going to be equal to 0. And f is going to be equal to 0 only at -5 and at 5. So it's just going to be at its endpoints. Okay, and so what is going to be... So then we want G of x. So G of 5. So G of -5, which is going to be equal... we don't know, because we don't know what G of x is. We only know what G prime of x is. But let's see right here. So has to be at x equals 5 though, because so G prime of x is equal to f of x, right? And G prime of x is always positive. So G prime of x is always positive, which means the graph of G is always increasing from -5 to 5. And so that means that so at what value of x does G attain its absolute maximum on the closed interval? So x equals 5 because G prime of x, which is equal to f of x, is always positive. So G is always increasing. On -5 to 5. So that means that G of 5 has to be larger than G of -5. Yeah. Okay. There you go. Okay, and that should be everything for this homework.